So now we're going to work the second example. In this example, we have a satellite that's in orbit, and we know what the mass of this satellite is. So this whole thing back here has got a mass of 200 kilograms. And the whole thing's moving to the right at 2,200 meters per second. Then we blow it up with a small explosion, which causes the rear part right here to move backwards at 1,000 meters per second. We want to figure out what the forward part of the rocket or satellite, whatever this thing is doing. So my guess is that it's going to speed up going to the right. And again, I'm going to call that V2 prime. And that's the first thing that I'm asked to figure out is the velocity of that part of the satellite. So again, what I'm going to use is momentum conservation. And I can do that by figuring out how much momentum the system starts with. So this system all has a mass of 200 kilograms, and it's all moving at that velocity. So I don't have to make this too complicated. I can just multiply 200 kilograms by 2,200 meters per second, and that tells me the momentum of all this stuff, which is my entire system. So if you do the arithmetic on that, you get a number like 440,000, dramatic pause, Marics. That's a lot of Marics. And again, because momentum is conserved, I can say that that is going to equal the momentum of the system after the explosion. So this momentum for this must equal the momentum for all of this. So P system prime then. So this thing right here, I'm going to do that in blue. That's got a mass of 50 kilograms. And it's moving at a velocity of 1,000 meters per second. But we should probably consider the fact that it's moving to the left. I still like making right positive here because all this stuff is moving to the right. All this was moving to the right. So if something's moving to the left in this system, I need to remember to make it negative. So I'm going to say negative 1,000 meters per second. And then plus, well, if all of this has a mass of 200 kilograms and this has a mass of only 50 kilograms, the rest of this must have a mass of 150 kilograms. So 150 kilograms, and then it's all moving at velocity v2 prime. And then again, the momentum of the system is 440,000 Marics. So that's the number that doesn't change, the momentum of the whole system together. All right, so doing a little bit of algebra. 150 kilograms times V2 prime equals 440,000 Marics. And I'm just going to add all the stuff in blue to both sides. So if you do 50 times 1,000, you get like 50,000. So I'm going to do plus 50,000 Marics. And so 150 kilograms times V2 prime would be like 490,000 Marics. So if you divide both sides by 150, you get about 3,300 meters per second. Just rounding to the nearest significant figure, give or take. And then up here in my picture, I figured that was moving to the right. I got a positive answer for this, so I know that that thing is moving to the right. So it kind of makes sense that it's sped up because all this stuff got pushed backwards. All of this stuff must have gotten pushed forwards. So it makes sense that this arrow should be longer than that. All right, part B, determine the velocity of the center of mass of the system immediately after the explosion. Well, beforehand, if I just draw a dot for the center of mass right there, that dot must have been moving at 2,200 meters per second. Because everything in the system is moving at the same velocity, the center of the system must be moving at the same velocity. So after the explosion, well, I have no way of using all this information to figure out how fast the center of mass is moving, but I do know that the center of mass moves at a constant speed since momentum is conserved. So I'm going to say V center of mass equals 2200 meters per second because it's constant when momentum is conserved. And so that's a little trick to remember. And that's a trick that shows up a lot on the AP exam. All right, boom, things explode, go in different directions. Hey, what's the velocity of the center of the mass after all this stuff explodes? Well, it's the same as what it was before. So use the information when it's one object to determine the velocity of the center of mass, and just remember that it stays constant if momentum is conserved. And thus, we end example number 2.